sorry. Sorry, you're breaking up a little.
Am I?
Yeah, your sound is a little broken.
Because I'm at my university, so perhaps there is a bit of noise. But let me see if I can do something.
It's like just it's just good enough that we can basically hear. Yeah.
Yeah. The volume is okay, but.
Okay, so but the video fine? Perhaps I should turn off the screen, maybe, so the bandwidth is.
Oh, we don't have video.
Oh wait, I'm not on video. Okay, so then definitely doesn't. Yeah, okay, but let's see. I can turn it on. Hi, can you?
Hi.
Yeah. Hi, Bruno.
How's it going?
Good. So, right, I guess. Should I start, or can you hear me well?
Would you like to say something about yourself and what you are interested in?
Yeah, of course. Yeah. So my name is Bruno Gavranović. I'm here from Zagreb. I'm at the Faculty of Electrical Engineering and Computing here. I'm at my last year of masters, and I'm interested in many things, but functional programming, category theory, and deep learning, and concretely the intersection of all these three things. And I've been doing some work on this. I'm right now a part of the Applied Category Theory School that's running, and I think Thomas mentioned that Christian Williams is also a part of this, and I know you mentioned, but I don't know if he's here or how he's related, but I know that you mentioned it. So yeah, I'm generally interested in this categorical perspective. And
yeah,
right
so
now we are
Bruno, you know Christian Williams, or you've crossed paths with him or work with him?
I'm just saying I've crossed paths, and he's in the same school as I am right now in the Applied Category Theory. That's right.
Oh, cool.
Yeah.
Yeah, and Bruno mentioned Mike, so I was also surprised because Mike is also the student of John Bias, right? I'm not sure. You said something about it.
And I think I just said I'm aware of the guy, and I'm aware of all these people working on these things. But yeah, I haven't crossed paths with him.
Yeah, nice.
Cool.
Yeah. So what's the general, I would say, background of you? I mean, I assume you're all interested in this computational calculus, but I'm not sure what's the extent and the background.
Yeah, so I guess we mostly met each other with the central point being the RChain project, and so I think we pretty much have a good understanding of, at least I have a working understanding of like how the pi calculus works. I think Tomislav and Isaac are definitely more mathy than me. Jay, I don't know where you fall on that spectrum exactly. Yeah.
So they've been working with Haskell and language development for pi calculus anyway.
I'm a retired educator. I have a background in math and some training in computer science, and I'm learning category theory.
Bruno, maybe you can start with.
Okay. Yeah.
I would like to know what are the goals of your project, and how deep learning can be compositional, and of course I'm super interested how this is related to Connell's work of automatic differentiation.
Yeah, definitely. I can talk about this. So I would say there are two components to what I'm doing. One is the implementation of various aspects of neural network training in Haskell. And second one is the category theoretic work I'm doing right now on regularization of neural network training using category theory. So the first one is the first point I mentioned is the GitHub repo I have. And to put this into context, right now there is TensorFlow, PyTorch, and all these various deep learning frameworks that enable us to I would say, do gradient-based optimizations really efficiently and code it up. Well, right now, most of this stuff is in Python. I think this is a long-term, this is a problem since this is not based on solid foundations, and the solid foundations exist, namely in functional programming and category theory, and there is some work that sort of bridges the gap, but there's not a lot of papers, and one of these papers is Conal Elliott's simple essence of automatic differentiation. So the idea is, if you want to compose two differentiable maps, right, how do we do it? And turns out, I mean, if you are at least briefly familiar with deep learning, you maybe know that the concept of backpropagation, which is always introduced as a sort of mysterious and abstract thing. And if you look at implementations, they are all really ad hoc, inherently stateful, and don't really have any, I would say, clear implementations. You can sort of, you have all these, people say, oh, it's just the chain rule applied to something, but when you sort of want to generalize this, not from scalars and vectors, but to matrices and arbitrary tensors, you run into many problems that are, from what I see, solved in ad hoc ways. So what Conal is doing, he's presenting a functional, well, a categorical way of composing these maps using the Cartesian closed categories. And that's about it, but I say this is really powerful. So so what he presents is a way where you don't really have to worry about states or tapes, or there's all these various ways of remembering, of having this what's called a computational graph in deep learning, and all these ways of traversing and doing the reverse mode and the forward mode of output. He presents a nice clear picture where reverse mode is right associative differentiation in this context, and the forward mode is left, or maybe it's the opposite. I don't really remember. So this is how this fits in. Yeah.
So is it backpropagation, or is this something different? Is he using backpropagation?
Right. So what people usually say is backprop is reverse mode automatic differentiation. So I guess the idea is you can differentiate all these functions, so you have a composition of all these functions, and well, it's not just a composition. It's you can sort of look at it as a DAG. So the idea is different orders of association of this composition give you different performances, right? And in deep learning, you usually have like a scalar at the top, right? You have all these inputs, large tensors, matrices, and you have one number that is sort of the cost, that is the cost and the loss that you want to optimize. So it turns out when you do it in a specific way, I think is the right associative, you end up with a much better performance, and this is what's usually termed as backpropagation here. In other words, the reverse mode of autodiff.
Mm.
I guess you might also be familiar with this. I'm not sure how familiar you are.
Yeah, personally, I studied deep learning in school. That was my specialization. So I don't know, like, if you're trying to generalize it in a specific way. By backpropagation, yeah, I basically just mean the standard, using the chain rule to move back through all the different layers, and compute like the gradient descent method.
Right. So I guess so if you look at the chain rule, I mean, this is what he argues in the paper, and that's so maybe to first put it into context. Conal's autodiff is just a part of, I would say, a categorical perspective on deep learning. But when we go into this autodiff and we look at specifically his implementation, there is an interesting thing he argues, and he says, well, if you look at the chain rule, it's really not compositional, and if you look at, it's not the case that the derivative of the composition is the composition of the derivatives. That's not the case. You always have, if you have two functions, right, you always need to keep what's called in deep learning these activations. You need to keep them. And chain rule doesn't really tell you anything about how to store this. And then you have all this idea of needing to keep all this in memory and needing to free it. all these problems that I think the compiler should solve for us. So what kernel does is lets the compiler solve that for us with a very specific formulation of this derivative. I'm not sure how much sense this all makes. This is kind of abstract, and I'm waving my hands a lot. But yeah.
Do you have any like papers or anything that you could show some of the math?
All right, perhaps I can share the screen and maybe open it up, but maybe just to also put the general. Yeah. So yeah, okay. Yeah, I can do that. Let's see. Share screen. Share my screen. Can you see this?
Yeah.
Okay, great. So let me just see. Okay, so here's the paper he's talking about. This is this thing, and again, what he says is that there is this sort of sequence of steps at two levels, right? We are, and he argues that we should, as he says here, to have just the programming language and omit the graphs and networks altogether. So we have this two-step thing where we write our neural networks in Python, but not just in Python, in a high-level framework which does a lot of the things that the compiler is duplicating the effort, is doing a lot of the things that the compiler is doing. So he just argues we should join this, and he terms this as differentiable functional programming. And now going further, he talks really about what's a derivative, and maybe we can go. He says, right, this is the, let me see. So here's the normal. Can you see this clearly? Is it maybe blurry?
Yeah.
Yeah, it's good.
Okay. So I'm trying to think of maybe a good way to approximate it. So what he says is he's not talking really about, as he says here, derivative of function of some a to b is not a number, a vector, but a sort of a linear map or a linear transformation. And all these vectors and matrices have different representations. So the idea is how can we compose these derivatives? So he first presents one way of derivatives. So he says derivative of a function. So there is one argument, and it returns, and it's a derivative in a point, right? So in a point A of this function, it's a linear map, right? So for any point A of any function, you get a linear map. And now there is this sequence of steps he's going through in order to, I would say, make it simpler. And he makes it analogous to the chain rule, which, as I said, if you have a f which is from A to B and g which is from B to C, it's not the case, right, that the derivative of compositions is the composition of the derivatives, right? You also have this f of A, right, which is the activation. So he says theorem 1 is not a compositional recipe. It's not the case that you can construct the derivative solely from this. And now he says there is a simple way to restore, and to put this again into context, this tiny thing is, and this is my impression, is the needed construct to do all these categorical clean things and to be able to, I would say, scale this more nicely without having to worry about keeping these activations. So he says, right, yeah, maybe is there any questions so far?
So you're talking about somewhere it said augmenting f with its derivative. So does that mean like when you're defining a function, part of defining it is also like specifying its derivative along with it?
Right, yeah, exactly.
You said that you put this function inside the context, and with that it becomes composition.
I'm not sure what do you mean by the context. I don't think I've meant that.
Okay.
It's not maybe a context. So let's go exactly as he goes through the paper. So he says, right, So the problem is we need this FA, right? We cannot just keep the derivative separately. We need to keep this activation. So he says, okay, let's take a first step. Let's just keep, given a function, right? We're not going to just remember the derivative, but we're just going to also keep here the function itself. Like it's the stupidest thing you can think of, augmenting, right? And then he says, okay, this is compositional because now you can reconstruct the chain rule. You have this F, right? But now he says, okay, but there is an efficiency problem because there is all this, right? You're doing all these computations many times, and in deep learning, this is a big problem. You want to start to eliminate redundant computation. So what he says is basically you can join. I mean, this is also very simple. Like these steps are very simple, one by one, but the end result is interesting. So instead of having, well, maybe I'm going to scroll up. Instead of having A to B and A to the linear map, he just says A to B times the linear map, right? And so this is sort of, so now given a function, in order to do deep learning, given a function, we just basically need to know also what is derivative, but he encodes this in a special form where he just given an A, you get an output, and also a linear map from A to B in this point, right?
Okay.
So and then the idea is you can continue building these structures, right? So the chain rule is a sequential composition, but there is a parallel version, well, not of the chain rule, but it's just parallel composition of these functions, which is very trivial, right? As you can see, it's just parallel. And now he says the derivatives work out nicely with this, and then he tells you, right, well, for all the linear functions, right, the derivative of this is just the f, which is kind of obvious, and then he builds the pieces together, and this is what my repository. I mean, this is just the implementation along with some other things of this functional view of differentiation, because this turns out to be a category. And okay, so this is just the definition of a category, but he shows, right? So he shows you can form a category with this, and it satisfies associativity, unitality, and then you can go build other things. Is this? Yeah, I guess, is this clear? Are you familiar with this so far?
Yeah, it looks really exciting, but maybe we could, if other people are willing to focus on that first theorem and try to understand. I'm kind of just trying to understand the jump from not being compositional to being compositional.
And for me, can you also say something about the chain rule?
Okay, yeah, I can try. So let's go back. So right, so the chain rule here, and this is perhaps a different depiction of what maybe usually would be, the usual. I'm just trying to open that. Right, so what would usually be, well, maybe this is the better one. So what would usually be shown as this, right? This is maybe the best. So if you have two functions, and perhaps a graph would be even simpler. But if you have two functions, this is f and this is g, right? In order to if you know the derivatives of both of those, well, you can derive f, of course, and get the derivative. You can derive g, but to derive the composition, right? You need to derive the last one with respect to its input, which is the output of one of these functions. So this here and what he shows us here are the same things. So given two functions from A to B and G from B to C, we know the derivative should be this type, right? Okay. And we know that we have to keep this activation. So the issue is maybe that the chain rule doesn't tell us anything about how to implement these activations.
Okay, thanks.
Is this, yeah. So again, to put this into context, this is I would say a tiny thing, that he proposes, just to join the function and the derivative together. Sorry, where this is, as he shows here, right, better here, and this enables us to eliminate the redundant computation, as he says here. But the main idea is that this enables us to make this a category. And then this enables us to make it monoidal and Cartesian and co-Cartesian and to build all these other things. Yeah.
Mm. I remember from his lectures that you can also use this when you go in reverse. So I'm not understand. I don't understand how this works, but can you say something about that? So you build your whole composition, right? And you can go from the back to the top, right? Because you memorized this function. And
and like regular backpropagation. You mean that? Like just using the chain?
Right. I get. Right. So as I get it, what might be confusing. So I'm gonna go here. So he says this is his, I would say, main description. But in backprop, right? You don't have A to B, right? You have B. You have the other direction, right? So this is I understand the confusion. So this is the first step that he's doing, and in deep learning, you have these two perspectives. Can you see me while I'm sharing the screen, or no?
Yeah. You see it.
Okay, so you have the perspective. You have the perspective going in one way, where values flow in one direction, but gradients flow in the other direction. But if you look at, okay,
no, I see.
Yeah. So if you look at this function, right, you have values flowing in one direction, but you also have gradients flowing in the same direction. So the question is, what's going on? And we're going to get to this. This is the interesting bit. So maybe I will actually go to this part right now. So he puts the pieces together, makes this a category and everything. But now he makes this monoidal. Basically, he says you can do this in parallel, and he shows this is all coherent. And he says, okay, this is. Now, one interesting thing is, okay, he shows you can do negation, but I'm trying to find where he's. Okay, so this is still, I would say, in one direction. Everything's going in one direction. But wait, right? So this is our thing. He's going to consider, in order to consider the other direction, we're going to generalize this differentiation that we have written so far. So instead of having the category of linear maps here, he's gonna have any category that satisfies certain laws here. So if you recall, this is the same thing as from before. Instead of linear maps here, we have this K. And the idea is to use the other direction. He's gonna just use the opposite category of linear maps, and everything sort of fits together nicely. And it sort of has to be additive, and there are some constraints. But given if you have a category already that satisfies some constraints, you can sort of have this. You can have the category of differentiable functions on top of it. Is this perhaps? So if you look at the composition, which is the most important part here, this is sort of best. Well, actually, I'm gonna open maybe Haskell, so it's easier to see, I think, because it's just clearly more nicely formatted. Can you see the screen?
Yes.
Okay. So I have this new type, generalized automatic differentiation, which basically takes in a category, which is modeled here as it takes a type and returns something, and two types A and B. So this is the formula from up there, right? From A, we get B, and we get also this A to B. Now, the interesting thing is the composition. Now, here's the instance for the category, right? And if you look at the composition of these things, right? So, like, this is kind of easy to write. We can just remove this. So we have F and G, right? And we know the result of this needs to take an A. Now, the only thing we can do is, since F is of type A to something, the only thing we can do is apply F, F to this. And then what we get out of this is, well, we're going to get, if you look at the definition, we're going to get a B and a derivative of f, right? So we get here a b and a derivative of f. And now since we have b, we can do the same thing. No, oops. I should have opened space max instead of this. But we get, when we apply g to this, come on, we get c and we get the derivative of g. And now to compose these things, I need to get formatting. Right, so the end result should be the type c. And now we have these two functions that we can just compose. And basically, or maybe the other way, let's see what was in the beginning, right? And then we get this. I guess, does this make sense so far? I've jumped into the very specific details already. Yeah.
Yeah, it makes sense, but not completely.
So, and that is the C that you return. Can you go back to the code?
Yeah.
Is the C that you return the original function, like B, it's the same as B?
So C is not a function, it's the value, some value. So given you know, if f is, I don't know, squaring a number and g is adding 2, then if I input 5, I would square it and get 25, and then add 2, and c would be 27 here, you know, like the value. But I would, yeah, but other than the value, I would also return the derivative of this.
Can we see this as a navigating in a graph, and this C is like a value in this point in the graph. So you know you're marking your path to this graph. Is this make sense? Or I'm not sure exactly how to think about it.
So yeah, like how would you compose these visually?
Oh yeah, so he has a visual representation of this. So exactly what he says is, by the way, since this all is a category, I think at one point he says, okay, I have this category that I've defined. Now I'm gonna have a functor from this category to the category of graphs, and then he just displays the graph, which is quite amazing, I would say. So this is also a category. I have to see what exactly is this example. I think it's up there. Okay. So he says, given an A and a B, I'm gonna square A, square B, and then add them. So there is always two paths of sorts. So given A and a B, you sort of have functions times, which takes both and returns them, and have function that squares them and then sums them up. Now this is just a function, but then he sort of shows the derivative of this. And now how to interpret this graph? I think this is the forward mode, in the sense that you don't see you cannot feel the reason easily about the backward one, especially since the function and its derivative are drawn separately. But I guess if you follow this around, you can see that given A and a B, you get an output, which is the output of the function, but also this function, which is to get an output and a linear map.
Okay.
So on the left side, there's two boxes that are labeled in. One's in that green box and one's not. Are those the same input values in both cases?
No, because if we look at, give me a second. Oops, where is the code? I have too many of these. Yeah. So the second in is this, right? So the first in is the A you get in, right? But the second in is the sort of the previous gradient of sorts, you know. Now, if you take it, yeah, so it's the gradient. You can think of the first in as the value and second one as the gradient.
Okay.
Yeah. I'm just gonna see my battery is almost dead, and I'm not gonna charge it, but I hope it's gonna hold. So yeah, and this is sort of what I've been working on in the. This is that's one component of deep learning, is just figuring out automatic differentiation. But sort of, as I say, I think on the repo, there is more components of this. There is a notion of a parameterized function, which can be also made categorical. And I feel this is very. I don't have too much time perhaps to go into details, but I would be happy to answer any questions. Yeah, maybe it's better this way.
Can you maybe say what do you mean by parameterized functions? But you're not talking about polymorphism.
Right. Yeah. No. So the problem is there is not really a term for this. It's kind of a new thing. But the idea is in deep learning, you have a neural network which takes in some image and gives you an output. Let's say, it takes a cat and returns an output if it's a cat or a dog. But the neural network is inherently parameterized. It has some parameter values. So in a sense, you want to be able. Well, I'm going to open the paper which talks just about this. Give me a second to show the picture. Right. So you have A is like the cat that you get in, and the B is the output of the network. But you also have this notion of parameters. And you want to be able to compose two networks in a usual way, right? If you have.
Are you showing something on the screen or?
I am. Do you not see it?
But no.
Okay.
I don't think you're sharing.
Right. I can. Can you see the screen?
Yeah. Yes.
Wait.
Okay.
So notion of parameterization comes from another paper called Backpropos functor, which presents a similar compositional perspective on supervised learning, and it tells us. Well, also, I believe this is. It tells us that if you consider a neural network as a sort of function that takes an A to B, it takes an image of a cat and it classifies it as a cat or a dog, but it's also inherently parameterized by P. And what you can always do, if you have two of these, you can compose them such that you keep the parameters separate. And this is all that parameterization, all that I mean by parameterization. If you have a network I that takes some cat, or something, and that gives you an output dependent on P, and you have another one that takes the output of the first and gives you something dependent on Q, you can compose those in a sense that you get a network that has the parameter space of the Cartesian product of P and Q.
Oh, I see. Okay.
So the parameters here are just like weights?
Yeah. Well, here it's abstract. It can be anything. I think they're talking about P as a set, right? But yeah, this would be weights. Your weights. Yeah.
Okay. Yeah, gotcha. Yeah, I feel like there's so many different things you can do with this. Like, this is kind of what neural networks need, is like a way to communicate with each other and their outputs to communicate or compose.
Yeah. So there is a very interesting perspective and that this Backpropos functor offers. Okay, I see my battery is at 6%, but I don't have a socket here. Do you mind I quickly go offline and come back? Because I think it might just die in the middle, and I wouldn't want that to happen.
Oh yeah, sure.
Yeah.
And we can also schedule for another meeting if you like, because this is a vast subject. So.
Yeah.
Sorry.
I said this is a big subject. Yeah.
Yeah, I actually think I would be a little better able to follow if I had some time to skim the paper and the repo on my own.
Yeah, would you post these papers in the chat?
Yeah, definitely. Yeah, that sounds like a great idea, and perhaps I could post them and have scan it and have any questions, and then perhaps prepare a more targeted outlook on this overview.
Yeah, sure.
Yeah.
Yeah, and I'm very unhappy with your audio today, so that will be much better,
Yeah. I'm curious. Have you heard of Have you heard of Chris Elias Smith, Bruno?
Have I heard of what? Sorry?
Canadian researcher, Chris Elias Smith. He worked on a project called
I
Spawn.
heard crystallized math at first. I was like, what?
Okay. Yeah, it's great for learning.
Sorry. No, I haven't heard. No.
He's this guy that talks a lot about semantic pointer architectures, and there's one specific idea about ways that you can represent ideas and compose, or if you treat a neural network like the output almost like a semantic pointer to the input, then you can compose these things. He basically defines, I think it's like a semi-group or something like that, on which you can compose together ideas. So you can bind like the idea of an agent with Alice by multiplying them together, and then you get a new vector. And you can combine that with the idea of like Alice chases by binding that with a verb and then adding the two together. I forget what it's exactly called. It might be like VSA or something, but there's kind of this general framework of people trying to like find ways to encode vectors and then compose them together.
You mean like, is it like pre-group grammar maybe?
Yeah, that's basically it.
I'm not familiar with his work, but I've read some, I would say, similar things, if I understand it correctly. Like, is it like parsing of natural language or not?
It's more like the inverse of it, where you're almost like getting syntactic representations through semantic representations. So like you're using neural networks, but you're able to bind them together in a way and compose them so that you can represent structural information. I can also post a paper on this. I was just curious if you knew much about it.
Yeah, please. That sounds interesting.
Yep.
Cool.
By composition, you mean taking separate neural networks and combining them?
Yeah, in this case, it's not so much composition as it is, he defines a few operations that you can do on the outputs of neural networks, where you can later take the inverses and like refine them. So you could build up a pointer that's really just a binding of a whole bunch of different neural networks that bind the idea of Alice chases cat or something like that. And then later you could query that vector by saying who's the agent in this idea, and it would return Alice, or who's being chased, the cat, things like that. But I mean, yeah, it's cool. Like this kind of stuff is cool because in the neural network space, you don't see a lot of, you see either like the symbolists or the connectionists, and you see a lot of semantic work being done right now, but it's all like kind of black box magic. And so I think, what the really powerful stuff is when you can kind of combine back the structural syntax on top of these semantics.
So you're putting it on a kind of relational memory.
Yeah, that's one way to look at it.
Yeah, I guess the bigger context for this is that there is so many components of a modern deep learning system that are learned, right? If you look at generative adversarial networks, which learn the cost function, or there is a paper called Learning to Learn by gradient descent, which learns the optimization procedure. There's all these parts of a deep learning system that are learned, and the invariants are quite hard to describe, it's really abstract. And when I'm exploring the speculation that category theory can be used to describe all these invariants. But this is like nobody knows really too much about this. And there's just a couple of papers exploring this.
Cool.
Yeah, I'm happy to talk more. And there's many different, I would say, perspectives on this. And of course, neural network is one of them. But yeah, I hope to learn more. And I'm sure you all know more as well. So I'll be happy to talk more. have a conversation about this.
Yeah, thanks for showing us this.
Yeah,
Yeah,
great,
thanks.
great to meet you, Bruno. And that was a cool introduction to deep learning. And as a side effect, I learned that Jay was interested in deep learning too.
Yeah.
Yeah.
Yeah. Thank you for having me. Yeah, I have to run also, but I'll post these links and maybe we can take it from there.
Yeah, great.
Chat.
Yeah, sure. Thanks. See you next time.
Thank you.
Bye-bye.
Bye.
See you.
Thanks,
Bye.
Bruno.
Well, Isaac, I'm definitely down to see what you've been up to in K. I feel like it's been a really long time since I've seen what you've been working on.
Yeah, I have a lot of different things that I could show at this point, because one thing that became very clear to me is that the capture-free built-in substitution that they have in K framework just like is not enough for what I'm trying to do with it. So when you're matching on patterns like, say, a send, for example, so I'm listening on some quoted send, or rather I'm listening for something like a send, and then that's going to produce multiple bindings because there's bindings coming from the names matching, there's bindings coming from the, whatever process I have in the send, there's bindings from that as well. And I had no idea how to implement that in K framework. And it doesn't have a pattern matching that you can use in a straightforward way as far as I know. So what I started doing is just building my own substitution function, basically. I'm not going to show that because I think I have something a little bit cooler because I'm pretty sure I have at least working for relatively simple things, a well-defined notion of structural equivalence finally. And this is like something I thought was going to be really easy, and then it turned out to not be easy at all. And it took me a very long time to build it, but I have it working now, so I can show you some of that stuff. Let me get some windows open.
It's such a huge class of problems that seem like they're going to be easy and turn out to be super freaking hard.
Yeah. Just defining alpha equivalence was hard enough, and then structural equivalence is alpha equivalence plus all of our monoid laws for the part operator. So let's see here.
So you're saying that this binding, when you not only have just a variable, when you can have multiple variables from these bindings. Right?
Yeah.
So you need somehow to store the location, right?
Yeah, right. Because if I'm listening, like my example was originally, right? If I'm listening for a send, then I have to somehow store the bindings that are coming from the names matching, and also the bindings that are coming from the messages that are matching as well, right? So if I'm listening for a send that has, say, 2 messages or something like that, well, I have a binding coming from the names, and I also have basically 2 bindings coming from the messages that I'm listening for, if that makes sense.
Yeah, like you're saying when you because you can pattern match on some pretty complex shit, and that's going to give you a lot of bindings that might not all be like found in exactly the same way, and you want to substitute those all in.
Right, exactly. And you destructure with pattern matching, right? So it's not that I'm listening for a send and then whatever I get that matches it, like, okay, great, go ahead and just replace that send syntactically wherever it appears in the body, and then you're good to go. It's like, well, I have these separate bindings that are coming from the names, and then they can show up wherever in the body, and then the messages can show up wherever.
And individually disjoint from one another.
Yeah, totally destructured. And I had no idea how to handle that just with the built-in substitution. So that was kind of my motivation to start just building my own. And now it seems like I'm going to have to learn about the Z3 theorem prover, and also this SMT stuff, this satisfiability modulo theories. Apparently this is like a big area. I've never even heard of it until I started getting these errors by using this substitution function that I built, K-Framer keeps yelling at me that I don't have an SMT lib translation for it. I don't even know what that means yet, so I'll have to figure that out at some point.
I think you can get those on the dark web for
yeah. Do you think Silk Road sells SMT lib translations? All right, let's see. I got something up here.
But this will be like a good news to buy it on the dark web. But
yeah, it's a good thing I've been holding on to these rocks so I can buy some SMT lib translations. Silk Road. All right, so get rid of that so we can see it better. Boy, I don't really want to get into all of the alpha equivalent stuff because that's, I mean, its own entire module by itself, but I'll just kind of describe how the structural equivalence is built up from alpha equivalence. So let me just show you some of the semantics. I mean, because I'm just defining names for functions here. It's not really anything important. The first thing that I tried to do with this, or I guess the first necessary piece that I recognized was when I have several processes part together, and now this could be, you know, as few as one process, and then it's not really a par, it's just an individual process by itself, and arbitrarily many. And basically I was thinking to myself, well, I have to have some way of finding appearances of the same process in like a par of several processes. And the reason that I wanted to do that is because you can reformulate par, so it's a multi-set of processes in reality, but you can reformulate it into a set by basically saying, translate every occurrence of, so if I have some process that shows up multiple times, right? So if I have something like, you know, I don't know, just some process A paired with, you know, that same one paired with, I don't know, maybe a different one, and then some other one, and then maybe that same first one again. So I have, you know, 5 processes paired together, and 3 of them happen to be identical. Maybe they're just alpha equivalent. It doesn't really matter. And then these 2 are just completely separate from the first. But basically, I would want to translate something like this into a set that contains 3 elements, because I have 3 unique processes up to alpha equivalence. The first element of my set would be something like A and how many times it appears in the par, so 3 for A. And then the second one would be, well, I have another process B, it only appears once, so that would be the element in my set. And then I have another process C, and that only appears once. So this would be my set version of the multi-set that truly is the par of all 5 of these processes. Does that make sense?
Yeah, totally.
Yeah.
This is like the standard way to implement a multi-set, I think.
Yeah, cool. So K-Framer doesn't have a direct way of working with multisets. The only way to work with multisets is through cells, and then that just gets really cumbersome because it's hard to work directly with cells the way that I wanted to. But with sets, it's really easy. There's lots of built-in operations. So I was like, this is the way to go. I'm just going to translate everything into this type of set notation, basically.
Yeah, nice. So one of your invariants is that you should never have 2 elements in that set who have the same first item, I guess, right? Like it means something got messed up if you have like A3 and also A1 in the same.
Yeah, exactly. So I build up that notion in a few steps. And so basically the first step is just how in the world do I even count the appearances of a single process, right? So basically here I'm thinking of A as being the process that I'm trying to count the appearances of. and I'm going to count the appearances of A in some process B. Now, this could be, you know, several things put together. It might just be a single process. But basically, the definition is like, if it's a single process, then what I know it's a single process because here I've specifically said rule out that case where B is you know, several processes paired together, and my notation for that type is just par.
So is par makes sense. That's just going to tell me whether B is like a proper par with multiple processes. Is not bool, is that not bool is just how you spell like the Boolean operator not?
That's right. Yeah,
okay.
Exactly. Yeah. So I'm saying it's not the case that it is a par of several processes, right? So it's just a single process in terms of, you know, pars. So basically, I mean, it's relatively straightforward, right? If A is literally syntactically the same as B, so before I continue with that, I should say I'm thinking of everything as I've already applied some sort of De Bruijn indexing. Everything that was alpha equivalent is now syntactically equivalent, and I only need to check for syntactic equality, and that's what this equals K is about.
So is equal K is K part of the operator?
Yeah. So this is a built-in operator in K. So with K, just like with I think C, it's kind of the same way where everything is a class or an object or something. I'm not sure what the right terminology is, but either way, everything in K framework is something of type K. And so this is the equality operator on that syntactic category of K.
Yeah, cool.
Yeah, so basically it's just saying like whatever I see as the first process, I want to check if it's syntactically equal to whatever I see as the second process, right? And if it is, well, then A occurred in B once, so I return 1. If not, well, then it occurred 0 times, so I return 0.
So this is like the terminating case when B is like not a proper par.
Yeah, exactly. So yeah, right. Yeah, so B is just like an atomic thing from the perspective of par, and yeah, I just need to check syntactic equality in that case.
Yeah.
However, if B is, or so rather now not B, but the second argument, if it is a proper par, then what I want to do is, well, since I've defined it to be left associative, it could be left or right. It really doesn't matter what associativity you pick, but that's just what I've told K to interpret this operator as. So I'm going to start plucking off elements from the right side, basically, and saying this thing is not a proper par, right? So it's just a single process again.
So your par structure is like almost like a cons list where you have, well, I guess except it's maybe like, so like pars are binary trees, I guess is what I'm trying to say. So if you have a bunch of stuff parred together, you have a necessarily really lopsided binary tree, right?
That's right. Yeah.
Okay, cool. Yeah.
And so basically the thing is, since it's left associative, I can always pluck something off from the right because the parentheses all deeply nest on the left side of the par symbol. So B here, it could be a non-par process is what I've been calling it, or it could be a par of several processes. Doesn't really matter. Either way, the whole point is that C is kind of atomic from the viewpoint of the par operator. And so I'm going to do exactly the same thing. This is, like you said, this is kind of like cons, right? Except it's just coming from the right side instead of the left side. But either way, same idea. Yeah. So I'm just going to check if A is syntactically equivalent to C. If it is, well, then I'm going to add that to whatever my count for A and B is, right? So just recursively call that par count function. And if it's not, well, then I just don't add one more and I just return whatever, the par count is of A and B.
Yeah.
So just classic recursion. I'm just counting number of occurrences of things. Let me delete this because I know I'm going to forget. Try to compile it and it's going to yell at me and say I have undefined variables. Okay.
Can I ask you something? You now first want to create these helper functions, right?
Yeah.
So you can transform all of the rules, all of the syntactic rules in the as the rules of the set. So you can
Yes.
just show I have this set, it's equal to this set.
Yeah.
Structurally.
Yeah, so let me show you that part, because that part's really easy, right? So structural equivalence, it's just a binary relation, right? Like I take two processes and they're either structurally equivalent or they're not. But basically what I'm going to do is somehow by this complicated function setify and by this complicated process of debruning, right, I'm going to essentially turn this into some, this first process into some de Bruijn indexed thing, right? Like all of my bound variables are just going to basically be called bound with some number that indexes them. But either way, then, so once I turn this potential par, and that's how we're thinking about it, right? Is like, maybe this is like 10 processes paired together or something. I turn it into a set. Well, first I de Bruijnify it, right? I appropriately index all of the bound variables and everything. And then I turn that multiset into a set by basically finding the number of occurrences of each of the processes that appears in it. And then I just ask, well, and I do the same thing for the other argument as well. And then I just ask, is it a subset? So is the set that I created from the first one a subset of the second one? Okay, if it is, that's great. But I also need to check the other way around, right? Because I want set equality, not just set inclusion. And there's no built-in set equality, but if this set is so if A is a subset of B and B is a subset of A, that's set equality.
Mm-hmm.
Yeah, so that's all the structural equivalence stuff does after you've defined all your helper functions, right? Is like, okay, de Bruijnify this process, turn it into a set, de Bruijnify this process, turn it into a set, and now just check that I have set inclusion on both directions.
Yeah. So there you go. It was only 2 lines of code, right?
Yeah, I know. Well, I also had to define name equivalence, right? Which I'm not 100% sure this is what I ultimately will end up with. So what I'm thinking here is if they're quoted, well, then it's very easy because we already have a well-defined notion for that. However, since there are strict name variables that we're using in Rolang, we also have to deal with this unquoted name equivalence, and I'm not really sure how that notion translates to unquoted names. But basically what I'm thinking of is, if there are 2 variables, the only way for them to be name equivalent is for them to literally be equal to one another. And this is basically what I've put here with the condition that they can't be something that's quoted.
So what is it? What's an unquoted name?
Yeah, so like a name variable.
Oh, it's a name. It's a name that doesn't have an explicit at the beginning of it.
That's right.
Yeah, I see what you're saying.
Yeah,
okay.
yeah. So quote for me is the category of all processes that have an at symbol in front of it, basically.
Oh, okay, cool.
Yeah. So these are like the traditional names from the row calculus, but there are more names in Rolang because we have these variables as well for names.
Yeah. Oh, yeah, right.
Yeah, it's a real pain in the ass, quite frankly, but and especially having name variables and process variables is just awful, and only having one notion of identifier is just it's pretty terrible. But either way, I digress. So that was the first helper function. So the per count, pretty straightforward, just counting number of appearances of a process in some part processes. So this par remove is, I think, similarly straightforward in the sense that what I'm going to do is basically the same thing. So I'm looking for occurrences of A in some potentially part together list of processes. Maybe it's just a single one, maybe it's multiple. And what I'm going to do is, if this process A in the first argument appears in the second argument, then what I'm going to do is basically say, well, if it appears, then, well, just don't do anything. I need to return a process, so I'll return nil. It's kind of like a unit. And else, if these are totally different, well, then I'll just return the second one because this wasn't here, so therefore I can't remove anything. And so I'm basically trying to, look at, I shouldn't have deleted my list. Let me keep it here. So I'm looking at something like this, and I'm basically asking three different questions. Like, if I'm taking A as the first argument, what do I get as, so what should the result of something like par remove of A of that thing, right? So let me put this in here. So what I'm doing is every time I see an occurrence of that process in the first argument, what I want to do is remove it from the stuff that I have on the second side. I mean, that's basically what the second line will say is like, recursively define this over all of the processes that are in this part. But either way, so I see A here on the end, I'm going to remove it. I see, okay, that's not A, that's not A. I'm going to remove that, and I'm going to remove that. So I should end up with something like this in the end. And basically, the point of doing that is so I can create this set out of this part, basically, because I want to only count unique occurrences of each one of these processes. And I also want to reduce the size of my pard list, basically, as I recurse over it. So that's basically all this par remove thing is doing, is like, if that first argument is in the list in the second argument, then go ahead and remove it. And if it's not, well, then really just don't do anything.
Can I ask something about K framework?
Sure.
You have two different functions that works together, right?
Yeah.
They have the same arguments. And why do you have two functions and not only one function that can return you the result directly without checking if is this something that K framework
well, this may be a lack of knowledge on my part, and there may be a way to do what you're saying, but I'm not sure how to do it other than by defining these helper functions and then just calling them as I need them. So there's no notion of anonymous function in K framework as far as I'm aware. I'm not sure if that's related to the question that you're asking. But.
Yeah. I suspect that you don't have all the nice features. So
yeah, because there's almost nothing built into it. So it's all homebrew everything, basically. Yeah.
So Tomislav, this style reminds me of a style that I first encountered when I was learning Haskell, which was like defining different cases of a function based on pattern matching, where I can do like, I'm trying to think of an example now, like f of, so like if I'm taking have some function f that takes an option or a maybe as an argument, like I can do, f of some x, and then I can do f of none. And that sort of just reminded me of this. And so, or like, for example, a lot of times when I'm writing a recursive function, I'll do like f of the empty list is something, and then on the next line, like f of a list that's non-empty is something else, and it recurses. So this, I don't know, I guess that's never necessary in Haskell, but this style sort of just reminded me of that style.
Yeah, in a sense, you're folding over. And you need some kind of way of destructuring this data structure.
Yeah. Right? Yeah, so there's some kind of pattern matching that's going on with these like is par predicates that I'm using here, because it's at least identifying if this second argument is a par. And for me, a par is just a process paired with a process, but a par is also a process, right? So they can kind of nest to the left. But either way, I'm at least doing pattern matching on the type, but it's not saying anything about, well, when it is a par, like in this case, it could be a par, right? And I could even force that B is a par and have, multiple cases here or whatever. But then I don't gain any information about the actual structure of B. I just know it's a par. Now it could be two processes paired together, or it can be like 80 million processes paired together. it just recognizes that it is a par.
Yeah.
Yeah. So it's a little bit weird to work with, but maybe I just haven't mastered it yet.
Just cross my mind. If can you return a pair like a tuple?
Oh yeah, I mean, I can define any syntax that I want and then return anything as something that I've defined, basically. Yeah.
Okay, you must define.
Yeah, right. And so, yeah, all of this stuff is coming from the fact that I'm importing this, grounded row syntax, and I've shown you guys that grounded row stuff several times. So I'm importing my notion of process and name and par and all of this stuff from something that I've already defined in a different module that I just import.
Okay, so you don't have built-in tuples. You must define it.
No built-in tuples. Yeah.
Oh God, that's amazing.
No, it's even worse actually, because there's already syntax. So if I write anything that I've defined as a term, so like in like a Boolean or something, that's already built in. So I can write something like true like this in parentheses, right? And the parentheses mean exactly what you would think they mean. But then the second you define some notation that's like, these are my tokens or whatever for my parser, and I put some process in there and I know that Booleans are a process, well, hey, now there's a parser collision, because it can't tell me if it's this one that it should be or if it's this one that I defined, or there's just no notion of right. And so now what I need to do is say, hey, K-framework, like this is a new thing. I know you think it's already defined, and you're right, but it's a new thing. I'm going to call it a tuple, and I'm going to tell you to always carry this label of tuple with this thing, right? And so then it can distinguish these two things apart from one another.
Yeah.
So it's a little bit crazy, but it makes it all the more magical when things compile. Because so recently when I was trying to do this stuff with structural equivalence, I was getting these module circularity errors. And so you see how I'm importing these modules here, but like this alpha module that I imported here, well, that's defined somewhere else. It imports other modules, and it really doesn't like when I say import say struct into alpha and then import alpha into struct. It's like, wait a second, you're doing this weird circular referencing thing. You can't do that. So you have to, and now this is something that I'm learning the hard way, is my module management. Now I really need to figure out how to actually separate all of these definitions so they're like contained in modules in a good way so that there's no circularities. But I don't know. I guess it's just a hard lesson that everybody has to learn at some point.
Yeah, I'm wondering if there is some kind of theory about that.
Yeah, the way that this module import stuff works, it works through something called a push out. That's about as much as I can tell you, but basically it's like you have two categories. There's a canonical way to define a category that kind of contains both of these categories. Other than that, I can't really say a whole lot more, but they call it a push out, and they talk about it quite a lot on their GitHub and in papers and everything.
Oh, it's a part of a K-framework, like a documentation.
Yeah, I don't think it's a notion that they defined. I think it was already a predefined notion, but they use this notion of category push outs.
Okay, thanks.
Yeah. Yeah, all right. So the whole point of this par move thing was basically to just remove the appearances of this first argument from the second argument, essentially. And so then the third part is...
I get that, but I forgot why you wanted to do that.
Yeah, it's just to create this set, basically.
Oh,
so
we're getting to
maybe
that.
as we create the set, it'll become more obvious why I want to do that.
Cool.
So to create the set, well, hey, if there's no par going on whatsoever, right? So again, this not bool is par business. If there's no par and it's just an atomic thing from the perspective of par, well then, hey, there's only one occurrence of that particular process. Like, great, that's the set that I want, is that process, comma one.
Mm-hmm.
However, if it is a par, right, like this, and I'm saying here, this right one definitely is not a par. I need it to be atomic so I can do some well-defined notion of recursion. So we're saying this one is not a par. Well, if it's nil, well, then it basically isn't there anyway, so let's just totally forget about it. But either way, if it's not nil, then what I want to do is count the appearances of this B in the rest of the list that's there. If it's greater than 0, right, then what I'm going to do is basically recursively define the number that I associate with B. So this is like the number of appearances. It's already there once, so that's why the 1 is here. Then I need to count how many times it occurs in A. So when I do that, that's great. But I also need to, let me see, it's been a minute since I thought about this part. So I've defined this element of my set. Well, okay, so this set item business is like, I have a set and here is an explicitly displayed element of that set. But this entire thing, set item of stuff, is a set itself. And so then putting this set right next to it is saying that I'm going to do the union, but I need to do something before I do that union. So we're in the case, yeah, okay, never mind. No, we're not in that case. So we're in the case where B is not nil. All right, great. Yeah. We are in the case where B is not nil and B occurs in A more than 0 times.
Yeah.
Right, so there's at least 2 occurrences of B in this particular.
Yeah, so B occurs in A means like this thing that's on the end that we're looking at as our current item is not unique in the par.
That's right. Yeah, and we capture that with that statement.
Okay.
So basically, I'm adjusting the right. So we count the number of appearances of B. Mm-hmm. That's great. Okay, so we have that element now. And what I need to do is remove all of those B's from A because I don't want to do recursion over the same exact thing again, right? Like, this is my answer and I want it to stay the answer. So I'm going to go ahead and just remove all of those occurrences of B that I just counted. And then this thing is a little bit goofy, but I had to put it here because I have this return of nil in the case where A doesn't occur in B, basically. Or rather, in this case, B doesn't occur in A because I've switched the order around a little bit. But either way, so it's basically just recursion, right? It's just like, okay, count the number of appearances of B. That's great. Now remove all of them, and the element that I want in my set is that number of occurrences of B with that process B. And then I also need to union together, doing the same process for all of the other stuff that exists, right? So now I've removed all of these B processes. There may be other processes there, and I need to recurse over that. So that's basically what's going on here.
Yeah, that makes sense.
That makes sense? Okay, cool.
Yeah, it does.
And then the other case here was just that if the par count was equal to 0, so B uniquely appeared at the end of the list here, well then it just is, so the set element is just going to be B comma 1, and then I need to recurse over the rest of the stuff in the par, but I also have to remove this nil comma 1 because again I added it up here by basically checking this silly case.
Yeah.
Can I say that this is not completely optimal, right? Because you
I doubt it's even close.
Just for my understanding, you're not supplying the number of elements in the function, right? You when you go and but it's maybe I'm wrong. because these elements are always different, right?
Yeah. So I try to do, see, I don't even know if this is just for optimization's sake or for correctness sake, removing these elements from the remaining bit. I couldn't think of a way to do it without removing them. So, I mean, at least to me, it makes sense to remove them, but also removing them does do some sort of optimization, because then I don't have to recheck things that I should have already checked, if that makes any sense.
Yeah.
And I think I have to do fewer lookups with this particular thing, but I'm not 100% sure. I haven't looked into it all that much. Yeah, and then so that's basically it. So if you understand how the par count, which is pretty straightforward, the par remove, which is also pretty straightforward, setify is a little bit convoluted, but if you understand how all three of those things work, and I think you do intuitively, because intuitively it's super easy how to do this.
They're named well. That helps a lot.
Oh yeah, great. Okay, cool. And then structural equivalence is essentially just combining these functions, right? Well, okay, so everything is combined into setify. So calling setify combines all three of them anyways. But then really we would just have to talk about this De Bruijn function, which I don't think I want to get into because it's just too obscenely long of a definition to talk about right now. But the idea is that when I put some Erlang program into our node, it's going to give me back some De Bruijn indexed thing, right? And I am going to return that same thing with this De Bruijn function. So that's basically the whole point of this De Bruijn function. Either way, and then the 0 is just telling me start the index count at 0, and the empty map is saying like, well, I haven't bound any symbols to any particular like bound values or whatever. But then this structural equivalence is just saying, okay, turn each De Bruijnified process into a set and then check that those sets are equal, right?
And you're not checking if this is not a par.
Yeah.
Where do you go in the nesting and comparing these other processes?
Yeah. So you're saying if P and Q are not pars?
Yeah.
Yeah, so if P and Q are not pars, then this is all really, really easy, because basically we'll just, for the setify function, return the set that contains just that element A, comma 1, right? It appeared one time in the par, whatever that even means.
Oh, so this is the way where you check all of the nesting inside the process, right? I mean, you can have a par which also is a par.
Yeah.
Or I mean, you can have receive, and in continuation you can have pars.
Oh
Where
man,
do you go?
I don't go anywhere with that because I'm not sure that. So this might be the through the looking glass business, where I'm not checking to see if within a receive, in the body of that receive, if there's a par there, if that's structurally equivalent to maybe some other receive that has a par in it, it would have to be syntactically equivalent for the, well, it would have to be alpha equivalent at least. So like if the order of the par was different inside the receive, this would not capture it yet.
Okay.
Yeah.
Where's the part where you let's just assume that they are alpha equivalent. Where's the part where you handle that?
Yeah. So that's all handled just by looking at this De Bruijn indexing of the particular process. So then when I'm, recursing over the syntactic structure and giving an index to everything, those two things would be handled in the same way, or at least that's how I'm imagining it would happen. And maybe it's not, but
yeah, cool. So that happens in this bigger function that we haven't looked at yet.
Yeah, right.
Cool. I have another question. On like around line 45 and 46, or I guess just 45.
Yeah.
So you take, if B is nil, you're basically like not counting that in the set at all.
Yeah.
But you have other ground terms that are getting counted. Is that intentional?
Yeah, well, because if we have something like, so I'm saying, well, because nil is the unit of par, right? No other ground term is the unit of par. So if it were, an integer or a Boolean or a string or something like that, like they're ground terms, yes. But we need to consider them in this set that we're defining from the par. Whereas nil is literally a unit. It might as well just not be there.
Yeah. So, okay. Yeah. So I don't think I put sufficient thought into this when I was writing it in Roxy. So when you do imagine you have some like super interesting process, send something on X and another thing on Y, and they're all parred together. And then let's say they're all the same so far. And then at the end, it's like par, some ground term that's not nil, like par 6.
Yeah.
And then this other thing that I'm going to later compare for structural equivalence is all the same, par, hello world.
Yeah.
Those are not structurally equivalent, I guess.
Yeah. Right? That is my assumption, right? So if we had something like stuff par 1, stuff par 2, those are not structurally equivalent. Because for me, structural equivalence has to, so structural equivalence subsumes, I'm not sure if that's the right word, alpha equivalence, right? So like this guy so 1 needs to be alpha equivalent to 2, and that's just not the case, because alpha equivalents for those guys have to be, literally syntactic equality.
Right. So another way to phrase that is like, if I have two processes and I'm claiming that they're structurally equivalent, that means that using nothing but name substitution and the monoid rules, I should be able to make them alpha equivalent.
Yeah, right.
Or even, I guess if I'm allowing name substitution, I should even be able to make them identical.
Yeah, that's right. Yeah.
Yeah, okay. I think you're totally right. And now that I'm thinking about it, like, I'm using structural equivalence as the gatekeeper for like, do two things com. Well, if their channels are structurally equivalent, then they do. And if my two channels were what you typed there in 43 and 44, I would not want those to com.
Yeah, right. Yeah, because on this one you're hoping to get a 1 and some stuff, and on this one you're hoping to get a 2 and some stuff, right?
Yeah. Okay, cool. That was helpful for me.
Cool. Awesome.
Yeah, and I'm thinking about structural equivalence in a sense of deleting the syntax which is equal, right?
Mm-hmm.
Yeah.
Because you must write sequentially when you write the code, but you somehow need to say what syntax is not relevant to be distinguished.
Yeah, I think it's super subtle though, because if you're like actually executing those two processes that he had up there, they would execute identically, right? They would produce the same behavior, and it would be whatever the behavior of just the stuff was. But if you're using them, if you're trying to say like, hey, should something com over these channels, that's kind of a different question than do they behave the same.
Oh yeah, I wasn't even.
But in a sense of structural equivalency, you can write 1 par stub.
Yeah.
Yeah. Oh yeah.
You're removing exactly what you are doing here.
Yeah. Yeah. So let me show you. I have a couple examples. I think this one is probably the coolest out of it.
Because I remember that when Greg was saying that the syntax, the grammar is a generator. You can generate bunch of stuff that first of all is not a valid code, so you need some kind of structural equivalence to say these things are.
Yeah, right. Yeah, because you can just freely generate whatever code or syntax you want. But so in a case like this, I have two processes. Like here's the first one, right? There's some new statement, there's some send with all concrete processes, and a nil, and it's all part together basically. And over here, I have essentially the same stuff. I mean, we're talking about concrete processes, right? So these need to be syntactically the same for them to be alpha equivalent. There's no nil in this one, but this, I changed the order of the new statement, right? So I'm declaring the variable B first and then the variable A. But notice that these pars were flipped around because I don't have it to go inside of this new body and then, do structural equivalence there as well. I'm not sure how I would tell it to be done if I were to do something like that, but I think that's a thought for another time. But either way, so hopefully we can agree that this process, this new BA A star or star A par star B is alpha equivalent to this one, right? I just reordered the variables and then reordered the pars, so they should be alpha equivalent. According to the alpha equivalence predicate I wrote, they're alpha equivalent, so that's reassuring to some degree, I guess. Hopefully we can agree that this is certainly alpha equivalent to this, and then this one only just has this nil as well, and we could even put another, as many nils as we want, doesn't really matter because they're just going to get removed anyways. So these two things are alpha equivalent up to the order of the par, and that's exactly structural equivalence, right? Is like up to reordering the par and getting rid of nils, every piece should be alpha equivalent. So I mean, it's not going to be super interesting. Dang it, I need a terminal open. It's not going to be super interesting, but I can go ahead and just run this code and show you that it does work out. And then now we're working here.
So
and I don't want to, yeah.
While you're getting that set up, I was looking back for that wiki article about term normalization that you shared a while ago.
Yeah.
Because I don't think this is necessarily like, I don't have any opinion on whether this is a good design decision or not, but I remember that Kyle had a note in there, I think even in the comments. Oh, dude, nice.
Yeah.
Congrats. About how the order of variables that you're declaring in a new, so when you do like new A comma B, like those are not like that matters, or maybe I think he was saying that that's a congruence that he wasn't going to support.
Yeah. I faintly recall what you're talking about. I don't remember the specifics, but I know there was something about reordering and in instances where they planned on doing it and instances where they didn't plan on doing it.
So it says some equivalences that this is actually, so it's split into things we currently support, things we will not ever support, and things we don't currently support.
Yeah.
And the one that's not currently supported is that new x comma y in P desugars to new x in new y in P, and so therefore that order matters.
Yeah, so that would be different, right? Like if so if we wanted to so what I'm hearing you say is new A, B, and whatever is maybe equal or not equal, I'm not sure, or sugared for new A in new B in whatever.
Right.
So these are not the same, right?
Not structurally equivalent. Yeah.
Yeah, exactly. Yeah. And so for me, these aren't even alpha equivalent because
wow. Okay, cool.
Well, because the way that it's going to work is this will rename this to, for example, x0, and this will rename this to x1, but it's not going to nest those new statements, right? Whereas this one, it will rename this to x0 and it will rename this to x1. Indexing is done, they're not syntactically equivalent.
Yeah. Okay. I see what you're saying. So maybe the more subtle one that I was trying to get at is when you compare like new A, B, and P with new B, A, and P, are those structurally equivalent?
Not structural. Yes. So those should be structurally equivalent, right? I think I definitely will have to do some sort of, when I see a new statement, go inside the body and check that this body is structurally equivalent to this body. I'm not sure how I would do it, but I think I will have to do something like that. I'll have to at least go inside the body of the new statement. But then I wonder, because then if I have something like new, I don't know, whatever in maybe there's another new statement here in whatever in maybe there's another one here. It's like, I don't know how to tell it to stop, basically, but maybe it'll just be done at some point because you can't nest new statements forever. So maybe that's okay. Maybe I just tell it every time you see this new thing, go inside the body check. Yeah.
Yeah, well, I just wanted to call that back to your consciousness because, like,
cool.
because I think isn't your goal to like have your implementation match the co-op implementation?
Yeah, I mean, that's definitely one goal. But I think that, I think with the substitution function that I'm defining, as long as I can figure out what in the world SMT translations are, and I don't know, maybe even translate this substitution function to this SMT lib stuff, I think I can do the pattern matching as deeply nested as I want.
Nice.
Yeah, but I think there's a lot of work to do before I can do that.
Yeah.
And for this case, when you have nested news, if the only term inside is just this new, then it is structurally equal, because you can just pop it one level up, and there is nothing else to do. This is just a nested new. So in that sense, it must be structurally equal.
Yeah, but you don't want to just always pop those one level up, because sometimes you're specifically using them to control scope. Like, imagine if there was, new X in. Yeah.
But if you don't have anything else, there is no difference. It is like you have a function that returns another function, and I mean there is a law that says if you are accepting A and then return a function, and B and then return a function, and then return something, it's totally equal to the function that accepts a tuple of A and B.
Mm-hmm.
So in that sense, I think maybe it's equal.
So you're saying the nested new statements as opposed to like declaring two variables in one new statement? Yeah.
Well, like a carrying in functional programming.
Yeah.
If you receive a tuple, and then it's always the same as receiving two.
Oh yeah, I didn't really think about that, but new is kind of like that, right?
Yep.
Yeah, in the sense that you can define this, or I mean, I could define like without B there, and then just say new B in with all that stuff together like that. Yeah. So currently, this term is not even alpha equivalent to this, and I want to say that originally I wanted to make it alpha equivalent because it seems like it should be, but then probably from that article that Kyle wrote, I decided maybe I should just try to make this alpha equivalence work first, and then I'll worry about that stuff later. And I haven't gotten to the later yet. Yeah, and definitely in terms of R-node and co-op rolling, they are not alpha equivalent, so they can't possibly be structurally equivalent. But it seems like they should be, right? Because for all intents and purposes, they do the same thing, and even in terms of the execution that I've defined, they do exactly the same thing.
Yeah.
Right, because I mean, new's just binding variables. Like that's it. That's all it does.
Mm-hmm.
Yeah. Yep. All right. I think that's basically all I have to show right now. I can definitely show some more stuff next time. I won't be here next week though. We're going to be on a climbing trip again. But the week after, we could talk more about this stuff if you want to, or look at some of those tutorial languages like we were talking about before. Either one I'm completely open to.
Yeah, I would like to see this simple language.
Yeah, me too, because they have array references where you can how do I say it? Multi-dimensional array references, and they de-sugar it into, you know, one-dimensional array references, and I totally don't understand how they do it. So I'd really like someone else to look at that with me and
Oh, that'd be cool.
hopefully explain what in the world's going on.
Nice.
I wanted to ask you how they recommend to build this structural equivalence in general. Are they saying that the set is the way to go, and you know, or they have some other techniques or something?
So I want to say that maybe one of my biggest shortcomings, maybe it's not, maybe this is the wrong way to phrase it, but either way, I think one of my biggest faults as a researcher is I always think, how would I do this before I look at what anybody else has done? So I don't know because I've literally never looked, because I was just like, this should work. And then I just went ahead like a bulldozer and just, you know, plowed my own path. And I don't know if somebody's done it in 2 lines and it's really simple. I mean, maybe that's the case, but this seemed like the most intuitively obvious way for me to go about doing it, at least.
Yeah. I think this is the good way to go, you know.
It takes a lot of time, that's for sure.
But you know, it's not wasted time. You know, you're thinking about the problem. So
yeah, no, not wasted time. Definitely not. Just taking time. Yeah, good or bad. I don't know. Maybe it doesn't need a moral judgment, but yeah, certainly keeps you busy, I guess.
because I'm wondering, you know, if you don't use something like multi-set, like a built-in stuff.
Yeah.
What do you really need of this operation on a set? What is it like the really needed stuff? So this can be abstracted, and so you can say, okay, I will not use a set, but I have these few functions, and I can, you know, do everything, because you're using set item. You are checking existence in the set, right?
I was just checking inclusion, just like subset inclusion.
Mm. And creating, and you're creating set, right?
Yeah, right. Yep. Yeah, I mean, element-wise, right? So I guess I could have very well just built up my own notion of a set and then gone with that, but I figured that was kind of a minimal requirement, so I could use it.
Mm-hmm.
Yeah. All right. Cool. I got to run, guys. It's been cool. I'll like I said, I'll be around next week, but the following week for sure we can look at more stuff.
Cool.
All right.
Thanks.
Yep.
Thanks,
absolutely.
Isaac. That was good.
Oh, thanks. See you later, guys.
See you. Thanks, Jim. Bye-bye.
Thanks, Jim.
tool by which we can do it, but then it's kind of like, well, you're going to write on the wiki. It's actually supposed to be stuff that's actually pretty stable. In order to do that, you